Hello everyone. Today I will give you an overview of the basics of ramjet and scramjet. Scramjet combustion process is discussed at some length in the week 8 of this course, and this is a basic introduction to that. Yeah. To get a perspective, we will start with a discussion of a turbojet engine. Okay. As you all very well know, a turbojet engine has a compressor followed by a combustion chamber where enthalpy is added, then there is a turbine, and there is a nozzle through which the exhaust is expanded and thrust is produced. Of course, you can also say there is an intake of some form. So, air is taken in, goes to the compressor, compressed air goes to the combustion chamber, in the combustion chamber fuel is added, that is to add enthalpy at high pressure to the working medium, and then the combustion products are expanded through a turbine. The work produced by the turbine goes back to the compressor, okay, work turbine. Then the rest of the exhaust from the turbine is expanded through a nozzle producing thrust. So, there is thrust produced. Okay. Turbojet is not what you will see in a civilian aircraft. It is a turbofan engine that you will see in a civilian aircraft, but for the purposes of the current discussion, the turbojet is adequate. Turbojet is mostly used in supersonic civilian aircrafts which do not exist anymore. Concorde was operational for some time, but not anymore. But of course, many of the military engines, supersonic military aircrafts need turbojets. Yeah. Now, we all know that if you have an aircraft with a turbojet engine, you can start from ground at 0 Mach, accelerate to maybe Mach 1, 1.1, 1.2, maybe up to 1.5, and the engine has a certain performance envelope for this range of Mach numbers. So, you can start from Mach 0. That is, you can produce a positive thrust to accelerate a vehicle from Mach 0 to about Mach 1.2, 1.3. Yeah. This is a key point. Start from Mach 0 and accelerate. To accelerate, you need force, and therefore, at Mach 0 itself, the engine should be able to produce a positive thrust. Accelerate to supersonic Mach numbers. Please go and look it up. I think it's about 1.3, 1.4 and not more than that. Yeah. Now imagine the following scenario. Okay. Let's say you have accelerated up to Mach 1.3, you have accelerated up to Mach 1.5, maybe even Mach 2, and now you reach a point where there is enough kinetic energy in the stream that is entering the engine that by simply decelerating it from Mach 2 to Mach 0.4 or 0.3, enough pressures can be generated, okay, and into the stream fuel can be injected, enthalpy can be added and expanded through a nozzle to produce thrust. And suddenly we are looking at a possibility of a very simple, at least in principle, propulsion device which has no rotating parts. Okay. The point I am making is, imagine flying at Mach 2. Okay, you have started in a turbojet engine, you have accelerated and you have gone to Mach 2 or Mach 1.5. Now you suddenly realize that You do not need a compressor, you already have a lot of kinetic energy in the incoming stream. You can decelerate the stream, increase the pressure, add enthalpy and expand through a nozzle. So imagine flying at Mach greater than 1.5. Okay. The following possibility is created. So you have a supersonic stream which needs to be decelerated. So you have a converging nozzle. Okay. Remember that to decelerate a supersonic stream you need a converging nozzle. You have Mach greater than 1.5 or something like that. So you decelerate it to some Mach number, something like you also need you need to slightly expand so that you go to subsonic Mach numbers. Okay, maybe something like this. Okay. Now this is the diffuser till this point. Okay, and then you have a combustion chamber. You add fuel. You have the combustion chamber. Then you have a nozzle. Okay. So here Mach greater than 1.5, here Mach number is 0.3, 0.2, something like that, maybe even lower. Then you can expand through a nozzle. Now look at the simplicity of this propulsion device. It has no rotating parts, no compressor, no turbine, no complicated arrangement to transfer the power generated by the turbine to the compressor. It is extremely simple, and this is a ramjet. And why is it called a ramjet? The key word is ram, which refers to the pressure that is generated by deceleration, or what is called the ram effect. Deceleration of a supersonic stream. Of course, the obvious downside of this is that you must already be flying at supersonic Mach numbers to be able to generate positive thrust out of a ramjet. So you cannot have a ramjet engine and start from ground and accelerate to Mach 2. That is an obvious disadvantage. So for positive thrust, you need a Mach number of greater than 2. Okay. You must already be flying, therefore the ram effect is available to you. You decelerate the stream, decelerate the stream, increase the pressure, add enthalpy by adding fuel and expand through a nozzle producing thrust. Okay. So 0, not just 0 thrust at 0 Mach, there is no net positive thrust till you reach about Mach 2. Okay. But now if you are looking at a propulsion device which could be an aircraft like an SR-71 which had a sort of a hybrid turbojet ramjet kind of an engine, or you are considering weapon systems that you want to fly at very high Mach numbers, you can accelerate these vehicles to Mach 2 and then another simpler ramjet engine can take over, producing thrust, and the engine is extremely simple, at least in principle. It is a realizing a hardware which will operate the way you want is lot more involved and complicated, and you will see some of these challenges discussed in week 8, if not for ramjet, at least for scramjet. But in principle it is a very simple device. Yeah. So now you have a ramjet. Okay. Think of the following scheme. You have a turbojet, that is where you started. You go from turbojet to a ramjet. Turbojet goes from greater than or equal to 0 to about 1.5. Ramjet takes over at Mach number greater than 2. Now you want to accelerate further, and that is a quest. You want to fly faster and faster, and you want to have weapons that cannot be intercepted by any anti-missile kind of a device. Okay, so you want to have strategic advantage, and one way of having that strategic advantage is by flying faster and faster. You want to get to, you are asking yourselves, why can't I go to Mach 4? Why can't I go to Mach 5? Can I go to Mach 6? Beyond Mach 6 with Ramjet? There is a catch. What about going to greater than Mach 6 with Ramjet? As it turns out, we will see the reason why it is not possible, that you cannot, it is with a Ramjet kind of an arrangement, you cannot go to Mach greater than 6. You need what is called a supersonic ramjet, or a supersonic combustion ramjet, or a SCRAMJET. The SC stands for supersonic combustion ramjet. Okay. So we will go back to our previous page. See, in a ramjet you had a stream coming in at Mach 1.5, which was decelerated to Mach 0.3. Okay. And this deceleration usually is, it has to be done in a short distance. You cannot afford to have long nice diffuser arrangement, because the longer the device, higher is the weight, and therefore you need larger forces to keep that object afloat. So you need to decelerate and increase the pressure quickly without also losing too much of total pressure. Therefore it happens through a series of shocks. Okay. And therefore the static temperature rises as the stream is decelerated. Okay. So in a ramjet, okay, let us say a ramjet flying at Mach 2, flow decelerates to Mach 0.3. Okay. This implies a certain increase in static temperature. Now you try to go to Mach 6 in the same arrangement. So flow decelerates. Remember that you need to decelerate to roughly about the same Mach number, because your flame stabilization with the injection of the fuel and everything is designed so that the flame is stable at certain Mach number. Okay. If you decelerate to a higher Mach number, then the flame won't be stable. So you need to decelerate to about the same Mach number, implies a much higher increase in static temperature. You can go back to your gas dynamics tables and calculate how much is the increase in the static temperature in this scenario. Much higher increase in T static. So what is the problem with this? Now here comes the catch. Remember that any combustion reaction, let us take methane for simplicity, CH4 plus air, which is 2 moles of air is, I am sorry, 2 moles of oxygen comes with this many moles of air, gives you roughly, I am just using this for for this purpose alone. I am not saying the only products are CO2 and H2O. There will be other products, but primary products are CO2 and 2H2O. Okay. Let me write, this is CO2, HOH, 2 H2O are formed. Okay. These are the products. Okay. Now what has happened in this net reaction is 4 CH bonds were broken. Okay. The O, I think it's O double bond O, please go back and check. So you have O double bond O, O double bond O. So 4 bonds were broken here, 4 CH bonds were broken, 2 O double bond O bonds were broken, 2 C double bond O were formed, and 4 OH bonds were formed. Okay. So a set of bonds were broken, a set of bonds were formed, and bond breaking is an endothermic process. You heat methane, a mixture of methane and oxygen or air to high temperatures, the bonds, you have to provide an ignition, and in the process of the flame propagation the bonds break and new bonds form. Okay. Bond breaking is an endothermic process, bond formation is an exothermic process. So the product formation, the reactions responsible for formation of CO2 and H2O are exothermic. The reactions responsible for the decomposition of the fuel and the decomposition of the oxidizer are endothermic. And we say that combustion of methane is an exothermic reaction because the energy that is released, the exothermicity of the bond formation exceeds the endothermicity of the bond breaking, and therefore the reaction is net exothermic. Why am I bringing this up? Okay. The reason why I am bringing this up is now you have accelerated a stream from Mach 6, I am sorry, you decelerated a stream from Mach 6 to Mach 0.3. Okay. The T static is so high that C double bond O double bond O H O H cannot remain in this form. Remember that now the temperatures are so high, there is lot of energy available for these bonds also to be broken, and therefore this might remain as CO at some temperature, OH, H, O, maybe even carbon at extreme conditions. What is the problem? Now the problem is all these bonds, okay, at least in these two cases where there are bonds, the formation of these bonds are not exothermic enough for the net reaction to be exothermic. You see the problem here? The problem is you are adding fuel assuming that the reactions are net exothermic, and it is going to increase the enthalpy of the flowing stream or the working medium, but if the temperatures are so high that you add fuel and nothing happens, the fuel simply decomposes into radicals and there is no net addition of enthalpy. And when there is no net addition of enthalpy, if this stream expands through the nozzle, you will not produce any net thrust. Okay. So this is the catch in accelerating to Mach numbers greater than 6 in a ramjet. So what is the solution? Solution is do not decelerate, go from Mach greater than or equal to 6 to maybe whatever is acceptable, Mach 1 to 3 or something like that, okay, in the combustion chamber. So you again have a diffuser, which I am drawing in a very simple way, but an actual scramjet engine, if you see, it will look a lot more complicated. It will actually be attached to a vehicle body and have a complicated arrangement, and the flow will decelerate through a series of shock structures, and then you will have the combustion chamber, and then you will have the nozzle. Okay. So this is the vehicle body. Diffuser, combustion chamber, nozzle. Okay. And you add fuel, and if you expect enthalpy addition to happen because of fuel addition, the Mach number here is greater than 6, here also it should be greater than 1. Okay. So combustion happening, so you have not decelerated from Mach 6 to Mach 0.3, instead you have decelerated from Mach 6 to maybe Mach 1.5 or Mach 2, so that the static temperatures are not high, so that addition of fuel will lead to addition of enthalpy. The reaction will continue to remain net exothermic, adding enthalpy to the stream, and therefore when it is accelerated through a nozzle, positive thrust, net thrust can be produced. Okay. So the reason why this is the reason why a supersonic this is the reason why a ramjet for Mach greater than 6 is called a scramjet, because combustion happens under supersonic conditions. Supersonic combustion. And again, in principle, no rotating parts, therefore there is a lot of simplification of the propulsion device, but there are very serious, or not very serious, very difficult challenges brought about by the fact that the combustion should be conducted under supersonic conditions, and additional challenges because you have a vehicle made of metal flying at Mach 6, and the heat loads or the heat flux that comes to the surfaces and how it is dealt with, how the cooling is done, everything is a very big challenge. So ramjets and scramjets are in principle simpler propulsion devices than turbojets and turbofans, but realizing a hardware and making it work as intended is a big challenge, and both ISRO and DRDO have now successfully demonstrated a scramjet engine, and hopefully there is the challenges and how they are overcome. Several things will be discussed in week 8 lectures. Hope you will enjoy it. Thank you very much.